You ever seen a really complex system just stop? No crash, no big error message, just silence. Well, today we're going to pull back the curtain on the hidden culprit behind these kinds of mysterious freezes, a tricky little problem called a race condition. And to really get it, we need to start with a story.
Right, so it all starts, like all the best tech mysteries do, with a story. Once upon a time, there was this high-speed, multi-agent system. This thing was the absolute backbone of a massive global supply chain. It was a total marvel of modern engineering until one day, it wasn't.
That's right, the entire system just froze solid. Products weren't moving, updates weren't processing, and you can bet millions of dollars were on the line. But here's the really weird part. Nothing had technically crashed. The system was just stuck.
Okay, so let's put on our detective hats and diagnose this thing. What do you even call this kind of failure? This silent, kind of dangerous system freeze? Let's break that down right here in our first section.
This is exactly what the engineers were up against, a silent timeout. It's the spooky state where your software is still running, technically, but it's not actually doing anything. It's like the digital equivalent of being frozen in place. And let me tell you, it's one of the hardest problems to debug because there are no alarms going off, no red flags, just nothing.
So what in the world could cause such a bizarre problem? Well, that question takes us right to the heart of the matter. We're going to look at the anatomy of what's known as a race condition.
So, to put it simply, a race condition happens when two or more processes try to mess with the same thing at the exact same time. Imagine two people trying to edit the very same line in a Google Doc at the same millisecond. Who wins that fight? And maybe more importantly, what happens to the document? It's chaos.
And this is where the problem really scales. Just look at this. With one agent, everything's cool, latency is low, things are running smoothly. But as soon as you start adding more agents into the mix, well, coordination becomes a huge challenge. That latency just spikes, communication bottlenecks start to form, and the risk of one of these system freezes just goes through the roof.
What's happening here is that all this chaos creates what we call tightly coupled dependencies. In plain English, that means each agent becomes way too reliant on the others being in a very specific state at a very specific time. They lose their independence. And that makes the whole system incredibly fragile, where just one little hiccup can bring the whole thing crashing down.
And what does that little hiccup actually look like? Well, let's watch how one tiny failure can set off a pretty catastrophic domino effect.
Okay, here's the play-by-play. You've got two agents trying to update the same inventory file. Simple enough, right? Wrong, because there's no lock, no system to make them take turns. One agent's update just completely steamrolls the others. Now the system has conflicting data, it has no idea how to move forward, and boom, the entire pipeline grinds to a halt.
And this isn't just some small bug tucked away in a corner of the code. Oh no, this single conflict triggers these massive cascading effects. The failure of one tiny task just ripples outwards, stopping other tasks that depend on it, which in turn stops others, and pretty soon the entire enterprise pipeline is paralyzed.
The end result? Well, the original analysis put it perfectly. Costly operational downtime. And that's the bottom line, isn't it? This isn't some abstract technical puzzle. It's a direct hit to the business, and it costs real, serious money.
But here's the good news. It doesn't have to be this way. So let's move on to a much more optimistic section, shall we? How we can actually engineer systems for true resilience.
This right here shows the kind of mental shift we need to make. We've got to move away from that fragile, set it and forget it logic, where everything is all tangled up and tightly coupled. The goal is to build these resilient, self-healing systems that use smart tools like synchronization and file locks to manage themselves. So how do we actually do it? What's in the toolbox? Well, here are the building blocks. First, we need synchronization to coordinate all the actions. We need those explicit locks we just talked about to make sure only one agent can touch a resource at a time. And we need smarter ways for agents to talk to each other asynchronously, which just means they can send messages without having to wait for an immediate reply. That stops them from getting stuck just waiting around for each other.
All right, let's get practical. Let's turn all this knowledge into your own personal prevention playbook.
Just remember the core idea here. The ultimate goal isn't to stop agents from working at the same time. Not at all. It's to give them the right tools so they can work semi-independently, so they can do their jobs without tripping over each other, all while keeping the whole system state consistent and accurate. It's about controlled chaos.
So I want you to take a second and actually think about this. Based on everything we've just gone over, where is that hidden race condition lurking in your project? Not sure where to start? Here's where to look. Any shared resource is a potential hotspot. Is there a central database that everyone writes to? A single configuration file that multiple processes might try to update? Any piece of shared memory or state? That's your ground zero. That's where the trouble usually starts.
And I really want to leave you with this one final thought. A complex system is never just in a neutral state. It's not just running. It's either resilient because you deliberately and thoughtfully designed it that way, or it's simply waiting for the right conditions to fail. The choice, really, is yours.